This is our first video on magnetism, and I chose this picture to start the video because I always see how my students are amazed, and many do not know that the bottom we call the South Pole and the top we call the North Pole, and we call it North and South because when we take the compass, the actual North Pole is South and the South Pole is North. Because if we take the compass, the north will attract to the south. So where we call the North Pole, it's actually south, and where we call the South Pole, it's actually north. And what you see here in this picture are the magnetic field lines. The magnetic field lines are coming out of north. So you see right here, the lines are coming, maybe I'll draw them in yellow. So the lines are coming out of north, the magnetic field lines. They always will be coming out of north and get into the south. So for the magnets, you will have magnetic field lines. And actually, the magnetic field lines look, they didn't know, they chose to be the direction from north to south. What they did know is they took the iron filing, and iron filing is like little cramps of iron. So they put it on top of the paper, or they can cover the iron with the paper, and or the plastic. And so what they saw is all these lines. So this is when they chose the North Pole. Let's say this is the North Pole and this is the South Pole, and they said, okay, from the North Pole we're gonna say the magnetic field lines coming out, and to the South Pole they are getting into. And magnetic field lines cannot cross each other, so you see they don't cross each other. They actually will be perpendicular to the surface. And so here is another example on the right. Again, you have magnetic field lines coming out of the north, and it's just definition. They chose it to be out of the north and into the south. So the magnetic field lines will have the letter B, and is going to be measured in Tesla. So magnetic field is going to be measured in Teslas. So here are the pictures, and in one of them we see the magnetic field lines. They are coming out of north and getting into the south. So B again is going to be standing for magnetic field lines. And how do magnets become magnets, or how did they become magnets? So the magnetic field in non-magnetic materials is so let's say it all depends on the electron spin around its nucleus of an atom, and this spin creates the magnetic field. The electron in most objects spin in the random direction, and their magnetic forces cancel each other. So here in this picture, in the first one, you see that they're called magnetic domains. So every single air that you see, it's a magnetic domain. So you see, because electron in non-magnetic materials spin in random directions, overall they cancel each other's the magnetic field. But then in process of magnetic field, so if you place those electrons or the material in the magnetic field, then all those domains are going to be pointed in certain directions because the electron spin will be affected by the magnetic field. And this is where you get the North and the South Pole. The electron becomes magnetized, or the material becomes magnetized, because the molecules in magnets are arranged so that their electrons spin in the same direction. And so this would be in permanent magnet. So permanent magnets, they have spins in the same direction. So here is another example. 3 electrons aligned in different directions in a non-magnetic material. And in the magnetic material or magnetized material, or inside of the magnet, the 3 electrons are arranged in the same direction. And that makes from south to North Pole. So non-magnetized objects have their magnetic domains randomly pointing in all directions, and magnetic domains are in group or of atoms that have their magnetic poles pointing in the same direction. But materials that can become magnetized easier have many magnetic domains that can be rearranged quickly when a magnetized object is placed in the magnetic field. So in this picture, you also see paramagnetism, and paramagnetism refers to the materials like aluminum or platinum, which become magnetized in a magnetic field, but their magnetism disappears as or after the magnetic field is removed. But ferromagnetism refers to materials such as iron or nickel that can retain their magnetic properties when the magnetic field is removed. So at the bottom you see ferromagnetism, and on the top you see paramagnetism. So as they notice that some magnets can, or some materials can be magnetic, so those are permanent magnets, but you also can make magnets by applying the current through the material. So what they notice is when the charges are moving, or the current, which is the moving charges, when the current is present in the wire, there's also magnetic field. And to determine this magnetic field, you have to use the right-hand rule. So here in the picture, you see the right-hand rule. And if your thumb points the direction of the current, which is in red color, so you have the current. So here we have the current. So if your thumb points in the direction of the current, then your fingers will show the direction of the magnetic field. So the direction of the magnetic field in this wire is going to go in this direction. So if you ever have to determine the direction of the magnetic field in the wire, you have to know the direction of the current, then you wrap your fingers around the wire, and it only happens in the wire that has the current. So when moving charges will produce magnetic field. And another thing is magnetic field will produce moving charges, because when you place a conductor inside of the magnetic field, then the domain will be rearranged. That means there will be present current at the moment of the change of the magnetic field. So when the magnetic field is changing, you will have the motion of the charges, and then when you have the charges are moving, they will cause the magnetic field. And here you also see that when there is no current in the wire, then if you place all the compasses around the wire, then they all will point to the north. So maybe this was the north pole of the earth, and this was the south pole, and it will show you the direction of the north and south pole. But if you place, or if you apply the current, or let the current flow through the wire, then the magnetic field is going to be the compass will be aligned with the magnetic field direction. So you see the magnetic field direction is going to be in this way around the wire, and so the compass will actually show the direction of the magnetic field around the wire. So if you want to calculate the strength of the magnetic field around the wire, you have to use the formula, and this formula is B, where B is the magnetic field, and it equals to mu, and mu stands for permeability of the free space, and so in vacuum it's going to be 4 pi 10 to the negative 7. 2 pi is the constant, I is the current in the wire, and R in the denominator stands for the distance away, or the radius of the magnetic field, or it's the distance how far away from the magnet you are checking the magnetic field. And mu 2 pi together could be replaced with K, and K makes 2 10 to the negative 7. The confusing part in this section of AP Physics is that you will have a few different K variables or constants, so you need to know which one to plug in when. So in the formula that you will see or be given on AP exam, it's this formula, but you also can remember that mu is equal to 4 pi 10 to the negative 7, and 4 pi divided by 2 pi gives you 2, and then k is 2 10 to the negative 7 in this case. What they also notice is that if you place a charge, not just any charge, it has to be moving charge, then there is magnetic field acting on the charge, because the current is made of many different charges. So what you see is the magnetic field acting on each charge, or magnetic field acting on the current. So there are going to be two formulas that we have to look at when we place a charge in the magnetic field. So only magnetic field will act on the charge only if it is moving. So you have the charge of the object that is placed in the magnetic field, the velocity of that charge, and then the strength of the magnetic field, and sine of an angle between the magnetic field lines and the direction of the motion of the charge. And this way you can determine how much force is acting on that charge. And in our lessons, and I will also add links to this video where in the description, where you will be able to see how the charges react to the magnetic field when they are moving into the magnetic field. Another formula that I want you to know is the force acting on the wire with the current when you place this current or wire with the current in the magnetic field. So it's the last formula at the bottom. So what you have there is the current, then you have the length of the wire that with the current is located in the magnetic field, the strength of the magnetic field, and the angle between the direction of the current and the magnetic field lines. So this is how you calculate the force acting on the wire itself placed in the magnetic field. And then also I showed you one right-hand rule, but there are actually different right-hand rules. So the first right-hand rule that I showed you is the one that you see in the first column on the left. And that one is when you wrap your fingers, and that shows the direction of the magnetic field around the wire with the current. So if there's no current, there is no magnetic field. If there is current, there is magnetic field produced by this current. And the formula that we said that can be calculated, so you can calculate how strong this magnetic field is, mu sub 0 divided by 2 pi, and then you have how strong the current is and how far away from the current you measure, and so the distance at which point you measure. So this would be the distance, or r, I can call it r. And so if you want to measure, let's say at this point, this is how you would measure the magnetic field. Another interesting part for the magnetic field that you need to know is this. So we said that the magnetic field is going to be in this direction. So when the magnetic field coming toward you, think about it like arrows from the archer. So when the arrows are coming toward you, you will see the dot coming at you. And when the arrows are flying away from you, because the arrows have like these feathers on the back, so when you see the magnetic field going away from you, you see the crosses, like seeing the back of the arrows. So when they want to show the direction of the magnetic field around the current, then they don't have to show the wire the direction like of the loop of the magnetic field. All they can do is to show that on this side the magnetic field coming out of the page, and on the right side the magnetic field coming into the page, which makes the cross away from you. So as I mentioned, there will be different types of right-hand rules that you need to know. So the first right-hand rule that I showed you was the right-hand rule to show the direction of the magnetic field around the wire. So this is the first case. The second case is, now in the first case, we're talking about the magnetic field produced by the current. Now, what if you have current and you place it in the magnetic field? So if I have a current, so here is the wire, and I have a current floating in this direction. So here is the current. The magnetic field around this wire, based on what I just explained to you, is going to be coming out of the page on this case, on this side, coming into the page or away from you on that side. So it has its own magnetic field. Now, what if I take this current with a wire and place it inside of the magnetic field. And when I mean inside of a magnetic field, that means inside of the foreign magnetic field. Maybe there is a magnet right here that has the North Pole and that has the South Pole. Because there is a magnet, it has magnetic field lines going from the North Pole to the South Pole. And I want to see what's going to happen to the current with the wire with the current when you place it in the magnetic field. So what you do, you use the right hand. The right hand is different from the one that I just showed you earlier. In this case, what you do, you place your hand. So here is your hand. Your thumb is going to be pointing in this direction, and your fingers show point in the direction of the magnetic field. So your fingers show the direction of the magnetic field. And it's a flat hand. The thumb shows the direction of the current, so the magnetic field, and the force acting on the wire is going to be by the magnetic field that you placed into is going to be out of your palm. So let me say it this way: if you have a watch right here, that would be your hand. So your fingers would bend that way away from you. So maybe these are the knuckles. And so the force acting on the wire by the magnetic field, foreign magnetic field, is going to be out of your palm. So when you place a wire in the magnetic field, foreign magnetic field, the two magnetic fields, one is from the wire and the other one is from the one that is foreign, the blue color, will interact with each other, and there will be force acting on the wire, and this force is going to be out of the palm. So if they ever ask you the direction of the force acting on the wire placed in the magnetic field, foreign magnetic field, what you have to do is to say, to place your right hand aligned with the thumb point in the direction of the current. Your hand is flat and your fingers pointing in the direction of the magnetic field, and the force acting on the wire is going to be out of your palm. The same happens for a positive charge. So if you have a positive charge moving into the magnetic field, and again, only charges that are moving will be affected by the magnetic field. So again, I have the North and the South Pole. And let's say your charge is moving in this direction. So here is the velocity. And the magnetic field lines are going from north to south. You do exactly the same what you did with the wire. You point your thumb in the direction of the charge. Then your fingers are aligned with the magnetic field direction. So your hand is straight. So here the magnetic field, the direction of the charge is aligned with your thumb, and the force again is going to be acting out of your palm. So if they say here is the charge, it's a positive charge, in what direction will the force act on the charge when it enters a foreign magnetic field? And you will have to place your right hand the way I drew it in yellow, and align your thumb with the direction of the velocity. You align your fingers with straight fingers with the direction of the magnetic field, and the force acting on the wire is going to be out of your palm. And these are the rules for the right hand rule. So don't accidentally use your left hand. It has to be the right hand rule. So for the left hand, you could use the left hand, but the rules would be different. So if you follow the right hand directions and they place it correctly, you will find always the forces and direction of the magnetic field or velocity of the charged particles, or the direction of the current. We're going to do practice questions about this related to this topic. And so you always have to remember not accidentally use the left hand when you determine the directions of the force, current, charge, or magnetic field. There is a little trick about the charges. So if you had let's say again north and south, and the magnetic field lines are going from north to south, and you have a negative charge now. So the negative charge is still moving in the same direction as the positive charge used to move. Now, to use the right hand rule, you do the same thing. You place your thumb with the direction of the motion of the charge. So your thumb is pointing in the direction of the motion of the charge. Your fingers are still in the direction of the magnetic field. So you have the velocity, the magnetic field. Now, in order to determine the direction of the force acting on the negative charge, so if it was the positive charge in this case, then the force would be out of your palm. So for the positive charge, the force would be out of your palm, which means into the page, away from you in this case. But if it is a negative charge, then the force is going to be in opposite direction. So the force for the palm is into the page for the positive charge, out of the palm. The force for the negative charge would be in the opposite direction. So it's the back side of your hand, not out of your palm. It's in the other direction. So in this case, the force is going to be acting out of the page, coming toward you right now when you're looking at the screen. So the force acting on the negative charge is going to be toward you. So the key point to remember in this second rule, right hand rule, is when you place a charge into a foreign magnetic field, or if you place a wire with the current in the magnetic field, then there's going to be the force acting on that wire. And if you have a positive charge, or if you have a current, then they have the same right hand rule. The force is going to be acting out of your straight palm, so it's a straight palm right hand rule. And if you have a negative charge, then it's going to be in the opposite direction, away from the back of your hand. Then what if you take, this was the second rule, this is the third, next one is the third rule. What if you, so the first one, this is the second, and here is the third. So what if you take the wire and you wrap it around to make a coil? So here in the picture, in the third one, in the third rule, I have a coil. And the current is flowing from positive to negative. So the current is going this direction, then it goes to the down on the back, then again in this direction, then down in the back of the coil, right? And again this direction. So anywhere here in front, the current is going to be going up, and anywhere in the back, the current is going to be going down toward the negative side of the battery. So what you do to figure out which one of these, what you're going to create actually when you make when you wrap the coil around, or when you write the wire to create the coil, you're going to create a temporary magnet. For as long as there is a current in this wire, there will be a south and north pole. And to determine which one is north and which one is south for this coil, what you have to do is, actually let me show you something here. So if this is the direction of the current, then as the first law says, the magnetic field is going to be going in this direction, right? So what you see here, the magnetic field lines are getting into on this side. And for the other side, you see the current is floating down on the other side in the back. So what you see right there is the magnetic field lines are going to be going in the opposite direction. The magnetic field are going to be in the opposite direction. So what you see here, the magnetic field lines are coming out of. So if the magnetic field lines coming out of, this is the north side and the other one is the south side. But it's kind of difficult to see and explain and remember. So what I want you to remember is, in order to determine the magnetic field, the polarity, let's say this, the polarity of the temporary magnet, or the coil, what you have to do is place your right hand, you see like in the picture shows you, right hand, where your finger, the thumb, is gonna show the north side of the coil, and your fingers aligned with the direction of the current. So the direction of the current, if you see everywhere in front, they're going up. So your finger aligned with the direction of the current, your fingers, but your thumb points the direction where the north pole is going to be of this temporary magnet. So you see there are 3 different types of right hand rules. One is for the wire that carries the current, and that wire, you rub the fingers around to show the direction of the magnetic field. The other one is when you place the current, the charges inside of the foreign magnetic field, and what the direction the force is going to be acting on it. And the last rule is when you want to determine which side of the coil is going to be north and which one is going to be south. So when you place the charge in the magnetic field lines, then the charge is going to have force acting on it. So what I'm talking about is this picture right here, and I have a positive charge placed in the magnetic field lines, and the magnetic field lines are pointing away from me because I see these crosses right here. So the magnetic field lines away from me, and the charge has the direction of the red arrow. It tells you in what direction the charge is moving, and the force is showing you the force acting on the charge, because the charge changes its direction because the force is acting on it, so it's going to change its direction all the time. Then the motion of this charge in the magnetic field is going to be actually the circular motion. So in this case, what you have is the centripetal force is, yes, we're back to the centripetal force. So the centripetal force is going to be equal to the force acting on the charge. And if you set up in this formula, if you set up QVB, and the 90-degree angle takes away the sine of 90 equals to 1, is equal to mv squared over r, the centripetal force, then one of the v's is going to be cancelled, and what you have in here is the solution. The r, the radius of that motion, will depend on the mass of the charge, the velocity of the charge, the charge itself, and the strength of the magnetic field. So this formula is not given on any of the AP exams, but you have to understand that when you place the charge in the magnetic field, it's going to be changing its direction due to the force acting on it, and that direction is going to be always the circular motion. In that circular motion, the radius can be determined by setting up the magnetic field force equals to the centripetal force. Also, when you have 2 wires and each wire has a current, there is a magnetic field around each wire. When you place them next to each other, they interact with each other. So the magnetic field line of the wire on the right is coming out of the page. So coming out of the page on this side and getting into the page on the other side. And for the next wire, the magnetic field lines going into the page on this side and out of the page on that side. So when you have the magnetic field lines coming going away on one side and coming out of the other side, they almost like lock each other, they hug each other, they are attracted to each other. So these 2 wires will have the forces acting on them that will cause them to attract to each other. They will want to be glued to each other. And on the other hand, if you have, so in this case, I have the current up and the current up. In the other case, I have the current up and I have the current down. And when I place these 2 wires next to each other, they will repel from each other. To calculate how much force of repulsion or attraction between them, I can use a different formula. So this formula is, again, mu over 2 pi, and I have I1, I2, times the length that is in contact with each other, so the length of both wires that are in contact with the other wire's magnetic field. So it is mu, which is the permeability of the free space, and then I have divided by 2 pi, then I have the currents in both wires I1, I2 divided by how far they are from each other, which is the distance between them, and times L, the length of those wires that are in contact with each other. I didn't get a chance to record any of the problem solution and solving problems in this video, and I will do it in the next one. This video mostly was about what the magnetic fields, magnetic field lines are, how they are created, and how the right hand rule works. And thank you for watching this video. I will see you in the next one.